So I was told we're going to do this in English, which is actually convenient for me. I'm Israeli, but have been living in the US for the last 9 or so years, and so most of my presentations are in English these days. You know, I asked them, I hope you guys don't mind, I asked them to turn down the temperature here so nobody would fall asleep. So it's a little bit cold. It's actually the coldest room I've ever presented in. So the topic of this presentation is really how we deal with large volumes of data that's maybe distributed in multiple systems. Maybe it's not ready for analysis, it's dirty and things like that. Just a little bit of background, co-founded Dremio about 2.5 years ago. Prior to that was one of the first employees at a company called MapR, VP of product there. We'll talk a little bit about Apache Arrow in a second. It's a project that we started at Dremio about 1.5 years ago. Has since become, I'd say, an industry standard in terms of how data gets represented in memory for analytics. It's now a foundational component in everything from Spark, GPU databases, InfluxDB, the next version of MATLAB, the next version of Pandas, and so forth. So what are the kind of two motivating factors here? One, data science on modern data is incredibly hard. It's no longer a world where I can have my data in one CSV file or one Oracle database and just point my tools at that data source and everything's great, right? We have cloud storage like S3. We have NoSQL databases like Elasticsearch, MongoDB. We have Hadoop clusters and just data distributed across so many different places that are not necessarily, here's a high performance SQL interface and go at it, right? So that makes it really hard for companies. I was meeting recently with the heads of data at Airbnb, Twitch, a few other Bay Area companies, and they were saying that in today's world, you almost need a data engineer for every consumer of data in the organization. So for every data scientist or business analyst, you really need a full-time data engineer. And even those companies, who are willing to, maybe throw $1 million a year at some of these folks can't get to a 2-to-1 ratio, right? So we have a problem. We can't hire our way out of the complexity of data infrastructure. And at the same time, most organizations or most users want self-service, right? We've my 3 elementary school aged kids use Google all the time. So they go online, they ask a question, they get an answer, and then we come to work with years of experience in data, and it takes us weeks and months to get answers to questions, right? So I think all of us now are so used to this amazing experience in our personal lives with data, and then it's extremely frustrating in kind of our professional lives that we can't just ask whatever question we want and get an answer. And what it typically looks like is this, right? We have our data scientists. We're hungry for data. We use things like Python and all the stack in that world. Things like Pandas, TensorFlow, etc. Users of R, Jupyter notebooks, etc. And then at the bottom here, we have data in various places. Sometimes that's one data lake, something like S3 or Hadoop. In other cases, it's spread across many different systems. And so what typically happens is the data gets ETL'd through a lot of custom kind of development into a staging area. That could be a data lake like S3, Azure Data Lake Store, Azure Blob Store, Hadoop, etc. It's a lot of work, but then we try to query the data in that environment, and it's too slow, right? We, just running kind of a SQL engine on top of a data lake doesn't give us that interactive response time that we all want. And so we end up ETLing the data into these data marts. So we maybe use Redshift, or we use an on-prem store like Teradata. Maybe that's more in the US. SQL Server, Oracle, and so forth. And then even that's not fast enough. So what do? We create cubes, and we pre-aggregate the data in the data warehouse itself. We create aggregation tables, and then we extract the data into CSV files and into BI servers and things like that. And then finally, we get the performance that we want. But the challenge here with this picture is, first of all, just the complexity, the number of technologies, the amount of effort to keep this pipeline working, and then the number of copies of data we end up with, and all the cost and security risks that come with a dozen disconnected copies of data all over the place. But more interesting to me, the fact that when this is what the stack looks like, self-service is really just a dream, right? The user at the top can't do anything on their own. The less technical they are, the more that's true. They're really dependent on an engineer to do every single thing they want to do, right? And data engineering is constantly in this, trying to keep up with requests. Can you run this query for me? Can you do this for me? Can you get me this data? Can you bring these two things together? Can you join this? And so forth. And so we decided to create an open source project about 3 years ago. We started working on that, spent about 2 years building that. really focused on solving this problem, right? Creating a much more elegant solution to this, right? And so fundamentally, Dremio is, you can go to dremio.com/download it. You can go to GitHub and see the source code. Basically, hooks up to your different data sources. Oftentimes, that's kind of one data lake. So if you have all your data in something like S3 or Hadoop, that's kind of a classic use case. And then the tools at the top that people want to use for their analysis, whether it's Python, R, Jupyter, or maybe some BI tools like Tableau. The idea with this project is really to serve the needs of two different constituents in the organization. One is the data scientists and the business analysts, and one is the data engineers. And so on the side of the data scientists, it's really about providing kind of this integrated self-service experience where people can interactively discover and explore the data. They can also curate new data sets. So we have kind of a built-in data preparation interface where users can create new virtual data sets without creating any copies of data. Basically, they're creating views, and they can collaborate and share them with each other. And then in terms of making the life of the data engineer simpler, we've developed a number of kind of interesting technologies here. One of them is data reflections. Basically, it's our ability to create kind of effectively data structures similar to indexes or cubes that kind of run behind the scenes, and it can accelerate queries. So you can get orders of magnitude better performance than just having just a SQL engine. And then providing kind of what we call a vertically integrated query engine. So a query engine that can leverage these data reflections to provide the 100x performance speed up that you would want for interactive analysis. Can also analyze the raw data faster than many distributed engines, and then can also push down queries into the underlying sources. So if you have some of your data in systems like Elasticsearch, we can translate query plans into Elastic's query language, into Mongo's query language, into Oracle SQL dialect, and so forth, right? Doesn't apply to everything. If your data is in S3, then we've developed a really fast Parquet reader to, for example, consume Parquet files from S3. So the experience to the user, I'll show you a demo in a second here. We kind of like to think about it as similar to Google Docs for data. And what I mean by that is if you think of the Google Docs experience, or Office 365, where people can collaboratively create new documents and share them and so forth, we want to provide that experience to the data scientist, right? Where they can create new data sets, they can share them with their colleagues, they can build on top of each other. You can kind of browse that lineage graph that shows what data set was created from what other data set. And all of this happens without creating copies. So at the end of the day, these are just views underneath the hood. If you're technical, you can write SQL. Most of the people in this room can. You can actually define these new virtual data sets through SQL as well. And then there's a visual interface for curating data. So when you want to cast types or extract a zip code from an address or do things like that, sometimes it's easier to do it visually than to have to come up with the right regular expressions and things of that nature. In terms of the performance aspects, how do we take a scenario where you maybe have terabytes of data, maybe petabytes of data, and still want to have that interactive response time where you can use a Jupyter notebook and create a bar chart and get a response 2 seconds later. So a few things make that possible. One is an open source project we created called Apache Arrow. I'll talk about that in a second. The second thing is data reflections. These are the materializations of data that we can create in the data lake and automatically leverage those to accelerate queries. And then it's the native pushdowns, the ability to push down processing into the underlying sources if those sources have the data maybe indexed like Elastic or things of that nature. So before I jump into a demo here, just wanted to explain a little bit about Apache Arrow, which is kind of the foundation for this. So like I said, about 18 months ago, we created an open source project called Arrow. Jacques, who's my co-founder, is the PMC chair of that project. And what Arrow really was designed for, we realized there was a gap in the market in terms of, in the industry, in terms of having a standard way to represent data in memory for analytics. And so we basically developed the specification and some libraries, and we worked with Wes McKinney. I don't know if you guys know him. He's the creator of Pandas. Wrote the O'Reilly book on Pandas. At the time was working at 2 Sigma, and worked together on this new specification and set of libraries for columnar in-memory data. Really focused on doing it in a way that's very optimized for Intel CPUs with their SIMD instructions, so vectorized processing. That's the ability of the CPU to do the same operation on multiple values at the same time. and also for NVIDIA GPUs, for leveraging GPU acceleration when that's available. And it's designed to work with any programming language and also to support not just relational data, but also nested structures like maps, lists, and so forth. And then all development is done kind of through a consensus open source development model. And so I think last time I checked, we had about 102 contributors, various different organizations, so different programming languages have been contributed by different companies or different open source projects. This is kind of a small subset of the or of some of the projects that are now built on Apache Arrow. So just a few examples here. The integration between Spark and Python is now based on Arrow, and so that ability to go from a Spark data frame to a pandas data frame using the toPandas function in Spark, and vice versa, that's become about 20 to 50x faster in the latest release of Spark because of Arrow. Python is now based on, or the pandas library, which is the kind of the foundational data science library in Python. That's now based on Arrow. In fact, Wes is, outside of Dremio, is probably the top contributor to the project. And that's also the foundation for other components. You know, if you've used things like TensorFlow, for example, that's all sits on top of kind of pandas. Dremio, of course, is based on that. H2O.ai is an AI library that's based on that. Rise Lab, if you're familiar, that's the one of the labs at Berkeley. Originally, the lab developed Spark. They actually built an Arrow cache now inside of a project called Ray. And then InfluxDB recently contributed the Go driver for Arrow. That's their way of developing kind of a SQL-like interface on top of InfluxDB. Also exporting data from Influx to other systems. So the idea here was really to create a standard way to represent data in memory, and then not only for that to be beneficial to an individual project, like many of these projects, but also to provide a foundation for the future so that as projects are starting to talk to each other, because we're in a world of heterogeneous tools and environments, we can now do much faster processing between systems, right? If you think about it, in the past, we used ODBC, JDBC. That was kind of that, and still is the standard way in which systems can talk to each other, right? Or REST APIs. And that means going from, you know, here's a very high performance representation of data to I'm going to serialize and deserialize every single record. I'm going to pass it in an inefficient format over the wire. And so we end up spending 90% of our CPU time just on serialization and deserialization and kind of changing formats of data. So we wanted to completely change that and move to a world where there's a way that you can move a batch of 10,000 records as a whole from one system to another, and all these different systems work on that same structure of data. And so that's really what we're doing here. I was recently, just last week in London, meeting with one of our users, Dremio's users is one of the large banks there, and they use this system called KDB. It's a very, very fast time series database used in financial services and in trading. Specifically, that was a foreign exchange trading use case. It was really interesting because Arrow structures are actually very similar to some of these high-performance specialized systems for kind of in-memory processing. So with that, let me dive into and show you what it's what this looks like. So I'll show you kind of a demo of Dremio. Hopefully this will come up. So I'm dependent here on my VPN connection. So I've this is a Dremio cluster here. Hopefully this works. Okay, so this is right now I'm connected to a Dremio cluster that's running in the cloud. So this is just happens to be running on 4 instances on basically 4 VMs, right? Normally deployments tend to be bigger because people use this for larger volumes of data. And so what you can see here is you can see that we're connected here. This is the user interface. We're connected to a number of different data sources. So this is Azure Data Lake Store. I have an Elasticsearch cluster, a Hadoop environment, some other data sources here. Normally, our users would have, Dremio users would have, maybe one data lake, maybe a few other sources. But this is a demo cluster, so we've connected to lots of different things here. And I can browse data. So if I basically all the data, even if it's non-relational, gets exposed in the exact same way. So this is a database called Yelp inside this Mongo database. If I click on business, I dive into this one collection inside of MongoDB, and you can see it looks like just like a relational table. Every data set in the system has coordinates, so mongo.yelp.business is this one. Going back to the main screen here, we have spaces. So spaces are a place where we can create virtual data sets. And so if we're curating the data, if we're prepping the data, maybe for a project or maybe for a specific use case, we can create a new space. So let's go ahead and create a space here called Data Science Summit, DSS. And we'll pin that to the top here. Right now there's nothing in this space, of course, because I haven't done anything there. And then every user also has their own personal space. So as a user, if I want to upload a CSV file or an Excel spreadsheet and join it with my data in S3, very easily do that. So let's look at some very simple example. Let's say I'm an analyst working for the city of New York, and I want to do some analysis. I remember the word MTA being part of the metadata. And so I might use kind of the catalog here, search for MTA, and that reminds me that I have this data set here of the last 5 years of taxi trips in New York. So this is a data set of about 1 billion records, 1.03 billion. Every record represents one taxi trip. So I have the pickup time, drop-off time, number of passengers, the trip distance, and so forth. And at this point, I can do one of two things. I can start interacting with the data visually. So I might say, you know what, let's drop this column, let's make some changes, maybe share it with a colleague, so creating a new virtual data set. Or I can jump right into an analysis. And so if I'm a BI user, I can click on, say, this Tableau button here, and I can start interacting with this data visually through a BI tool. In a second, I'll show you how we do that programmatically through more as a Python user. So here I'm a less technical BI user. Maybe I know SQL. I can also do this through a SQL editor. And I can start aggregating. So I might do a count star on the number of records. And you see here 1.03 billion records. So if I was using something like Spark or Presto, something like that, this would be about 5 to 10 minutes per query. And so you can see that the queries are much, much faster than 5 to 10 minutes, right? They're coming back in less than a second. So this is an aggregation by year. You can see that the number of taxi trips has gone down from 2012 to 2014. That's probably because the Uber and Lyft became more popular in New York. I can look at the tip amounts. So I might look at what is the average tip amount for a taxi trip, and I'll change that to an average. Okay? And so you can see that tip amounts have gone up from 2009 to 2014. Let's change the color so it's easier to see. Okay? And I might say let's aggregate by month instead of by year. So let's change this to a month. And you can see that tips are higher. Taxi drivers get more tips later in the year than they do earlier in the year. Maybe people spend all their money on the holidays and kind of become cheap come the new year. And then July, a bunch of tourists in New York, they don't like to tip maybe, right? And so I can do all these different kinds of analysis. I can also do that exact same thing through a Jupyter notebook, right? So if I'm more of a Python user here, you can see I can run this query here, which is extracting the month. I'll make this bigger so it's easier to see. So I'm extracting the month from the drop-off time, and I'm aggregating, I'm selecting that column as well, I'm calling it month, and then counting the number of trips and the average tip amount, okay? So as I run this, you can see that that comes back very fast, right? Here's another example, loading it into a pandas data frame and doing a plot. Okay, and that's one example of a query that can be fast, where I'm doing aggregations. Another example is maybe I'm looking for all the taxi trips that occurred on a specific date. So I'm not looking to aggregate the data, I'm looking to just select specific records. So here I'm looking at the day, the number of passengers, and the total amount paid to the taxi driver for taxi trips that have this vendor ID and occurred on a specific date. But I'm only selecting the first 10 so I don't blow up my notebook here. So again, I run that and I get a very fast response time. And the reason I'm able to get this kind of fast response time, whereas normally if I was just using a distributed SQL engine, Spark, Presto, Drill, Hive, etc., is because we're using Apache Arrow to accelerate these queries and leverage kind of the modern Intel CPU instructions for more parallelism in the CPU. And then the second reason is that we have these data structures called data reflections. And so if I go here into the user interface, and all this thing is available through APIs as well, of course, you can see the queries that have come in from the tool. So in this case, I can look at, start with a simple example. So let's say this query here that came in where I was aggregating on the month. So this is the query that came, I think, from Tableau, right? So it's this ugly kind of SQL. And you can see, we say that the runtime here was less than a second, came from an ODBC client. And you can see it was accelerated by this reflection. So again, a reflection is a materialization of data that we maintain and update on a regular basis in the cache. And the cache in this case lives on S3. It can live on Azure Data Lake Store, it can live on HDFS, or just on the local disks of the Dremio cluster. And I can click on that and see what is this aggregation that we're leveraging here. So in this case, you can see we're leveraging this aggregation here that has the data pre-aggregated by the vendor ID, the pickup time, the drop-off time, the number of passengers, and a few other things. And so the idea here with these reflections is that the optimizer has various different representations of data in the system related to different data sets. Some of them may be partial aggregations, others may be the raw data, perhaps partitioned in a specific way. And then the optimizer is able to automatically figure out, using various algorithms, which reflections we can leverage at query time to accelerate this query, right? So if you think of how is Google fast? It's fast not, they don't just go use 5,000 machines and scan all the web pages when you go and search the web, right? They've prepared various data structures, various models, various indexes. And so the idea here is to create different materializations of data, not necessarily the raw data, maybe aggregations of some of the columns, maybe some of the columns partitioned in a specific way. And then have an optimizer that can automatically figure out when you submit a SQL query how to leverage those reflections, right? So that's what we're doing here, and that's what makes these queries so fast when the user is actually running a query. So if I go here, show you a few other examples. I have a set of notebooks here. These are just some setup functions for the notebook. What we're doing here is we're presenting all the data in virtual data sets and in the physical data sets in one namespace. So from the standpoint of the Jupyter Notebook, the Python user, or the Tableau user, or the Power BI user, Dremio appears like a relational database to the top. So it basically sees us like you would see a relational database. You can submit a query, get the answers, right? And so you can see the schemas here. DSS is one of the schemas in this system. Okay, I'm going to skip through a few things here. This is an example here where we're joining data across two different sources. So you can see here we're looking at a join between this data set. This is what we call a physical data set. So it's a table inside of Oracle and a table inside of Postgres. And so we're looking at the departments and the employees and doing a join on the department ID, and then looking for which department has the highest salaries. Okay, so this is a join between two sources. And basically, the way you do that in Dremio is every data source, every data set in the system has kind of coordinates. It's a dot separated path that allows me to specify that. So that could be a directory of Parquet files or CSV files on S3, and it could be an Oracle table, and it could be a Postgres table or an Elasticsearch index, right? At the end of the day, you just have to refer to it using that canonical kind of set of coordinates. So this is an example where we join these two things, and then we get the answer here. You can also leverage, depending on the data source. So for some data sources, we maintain more statistics than others, like number of records at a minimum, and things like that. And where we do have the statistics, we try to leverage them. I'd say right now, systems very good at that when it comes to like data lakes, like your Hive tables and things like that, including in the cloud. Okay at that on kind of the relational side, but there's more work we're doing now to improve the kind of the connection to relational databases. Other questions? By the way, I can hardly see anybody here because there's this light in my face.
Question about writing the data back.
Yeah.
Do you need to write the data back to the data source itself? Whoa. Do you need to write the data back to the data source, the original data source, or you can write it back to Dremio and it will propagate it to the data source?
Yeah, so when you're using the system, normally we don't write the data back anywhere. The reflections themselves, those materializations of data that we use as kind of an underlying kind of caching / indexing system / cubing system, we can store those in the data lake, like on S3 or HDFS or something like that, right? We don't normally write back into like an Oracle database, let's say. We do allow you to export data. So as an example, let's look here. Let's say I have this data source. I'll give you a very simple example here. So I had this data source of businesses. These are the businesses in the United States on the Yelp. Yelp is like a review website in the US. So this is mongo.yelp.business. I might say, you know what, I don't need this ID column, and maybe see the category, see the city here. Maybe I only need a subset of the cities for my analysis for building a model. So I only need Las Vegas and Phoenix for my model. So I'm going to do that. And maybe you see categories here. That's an array. Maybe I really don't want an array. I want to unnest that so I can like do a group by and figure out what's the most common business category. So I might say, let me unnest the categories. Okay. So instead of having an array, I want one category per record. I'm going to rename that. So basically all the changes that I'm doing here are virtual. So I haven't created any copy of data. It's basically I've created a view. In fact, if you open the SQL editor, you can actually see those changes in SQL. So you can see where city in Phoenix and Las Vegas, and you can see the flatten function here and the renaming of categories to category, right? These things that I've done. So if I save this now and I go and save this inside of the DSS space and I call this, let's say, categories, right? I can now access this data set, but I don't have to export the data. Okay, this is a virtual data set, and I can go query that data set. So let's say here, if I wanted to go to here and say query DSS dot, what did we call that, categories? So let's say I want to run this query here. So you can see I have this DSS dot categories is a new data set I just created in the DSS space, which you created at the beginning of the demo. And I can do that. And if I could go here and say, you know what, I want the address, I really want to do analysis by zip code. So maybe I want to look at the zip code here. So I can click on a zip code in one of these examples and click on extract. We try to recommend the regular expression that would be used to extract the zip code. If it doesn't work, you can flip the card here and provide that yourself. And then I'll rename that to zip. If I save that now, I'm basically saving a virtual data set. We version control all the changes. You always go back in time. But if I go back to my, where was my Jupyter environment? So if I go and rerun this query again, you should see now we have this new column called zip code. This is a calculated field, right? It's a virtual column. So I haven't materialized this anywhere. Now, if there was a data reflection, let's say on that original data, the categories data, even if that didn't include the zip code, that would still be okay. Like the reflection doesn't have to be the exact answer to the query that somebody's looking for. The optimizer will recognize that we can build on top of that and do a cheap calculation rather than kind of doing a more expensive calculation at runtime. That's a good question. So we have work. How do we know which reflections to create in advance? I'd say there's where we are today and where we're heading. So where we are today is that you can kind of, users are allowed to kind of vote, and they can say, you know what, like this let's say I'm a user using this DSS categories data set's too slow, so I can vote on this data set here, and then kind of the data engineer, the admin of the system, can kind of see what people are voting on. And we can make some basic recommendations today based on like cardinality of the columns, cardinality of the fields. What we want to do, though, that's where we're heading, is the ability to automatically figure out the right reflections to create. So think about it as an exercise in, we see all the history of queries, what people are doing. We understand them already very deeply at the relational algebra level, right? And then you might want to say, you know what, I'm going to allocate 10 terabytes of space on S3, let's say. Please figure out what's the best bang for the buck for given 10 terabytes of space. Now, there's always a challenge. Like we talk to companies about that kind of an approach, and they're always like, well, but the CFO has a dashboard they log into once every day. It's only the CFO uses it, so it's not going to be a common query that you're going to see, but it's the CFO, so it has to be fast, right? So we will always have the ability to manually define these as well, because it's not always that the most common thing is the most important thing to the company either. But certainly the next step is to make that much more automated in terms of kind of learning from user behavior.
What is the consistency model between reflections and original data?
Consistency model between original data and the reflections. So right now we allow you to define the reflections, the update schedule as the same for a given source. So you can't define for a given data source, two different data sets one is going to get updated hourly and once every 5 hours to avoid those types of problems. It's not atomical in any way, right? Even irrespective of that, it's not an atomical operation, so you do have to make sure that you're okay with, like any caching system, right? It's, things get updated when they get updated. But we do try to make sure that it makes sense. I didn't mention there's also a way, so Dremio can update and maintain these reflections automatically for you, and we'll use our engine to create them and so forth, and either incremental or full updates. You also have the ability now with the 2.0 release of the project to create your own reflections in like your own ETL tool. So you use Informatica or Spark or whatever you want to use to create some data set of Parquet files, let's say, and then you can register that with Dremio and say this directory of Parquet files in S3 or this Hive table represents this aggregation, and then we can then leverage that. And then it's up to you when you want to update it, how you want to update it. So that's more if you have kind of developers that can kind of do that, or maybe you already have a pipeline that does these things. We have 2 seconds left, so I think we're done. But I'll be outside afterwards, and also at the Twingo booth. They're representing us in Israel, so we can talk there.
Thank you very much.